POE students, here's your video on how to work through the Tensile testing document. First, what you're going to want to do is go ahead and secure your testing data. To find your testing data, you're going to go to the date 3/14 on the calendar. You'll click on the Material Testing Workday link, and under the details there are two links, one for period 7, one for period 8. Select on your period. That will go to a shared folder, and in that shared folder you're going to find your document. And you're just going to go ahead and right click and download that to your Google Drive. Once you have that document, you're going to go back to your tensile testing document right here, and you're going to go through and you're going to finish up the rest. So I threw some basic numbers in here to give you an idea. These aren't actually legitimate test data, but it's to give you an idea how to work through each of the equations. So I went through and I re-recorded my smallest measurement. I recorded my length between indexing dots. I used a dial caliper to measure between them after it was broken, and I got a, you can see there I got a difference of 0.533 from 0.521. Then I used a dial caliper to measure the necking region diameter, and that gave me 0.072. For number 11, it asks you to calculate the test sample's total strain. So to do that, you're going to take the difference between your indexing dot lengths, mine was 0.533 and 0.521, and then divide that by the original length, which is 0.533. Once you complete that equation, you're going to get your total strain. Mine was 0.023. Number 12 asks you to identify the test sample's ductility. To do that, you're just going to take your strain and multiply it by 100 to get a percentage. So mine was 0.023 times 100. I add 2.3%. Now, moving on, 13, it wants to calculate the test sample's reduction in area, and this is going to be a percent. So to do this, it's going to ask for the area original. So what was the original area minus the final area? You're going to divide that by the original area, and then multiply that by 100%. Don't multiply this first. This should actually be, these should also be in parentheses. So I'm going to go ahead and pause. I'll do this math, and then I'll show you what I got. Okay, so I had my original area, which the diameter was 0.090. The area for that was 0.0063585. The reduced area was 0.00406944, and that was from the 0.072 diameter. So I subtracted those. I divided by the original diameter again, and I multiplied that entire thing by 100, and I got a reduction of area of 36%. So that's number 13. Number 14 is you're just going to take a print screen of your completed tensile test and insert the graph into the test sample calculations table. So I took a screenshot for number 1. This is my graph. You want to take a screenshot of your graph, and I placed a screenshot into every single problem where it asks for the graph, all the way to 7. Then, on top of that, if I go back to number 1, it's going to pretty much tell me what to do. I'm going to calculate the proportional limit stress. So it says locate the proportional limit on the graph, the test graph, and solve for the proportional limit stress, which is going to be force divided by area. So in this case, the graph that we get is not a stress strain graph, but a load elongation graph. So we're going to use this to calculate our parts of the stress strain curve. So the first thing is we're going to locate the proportional limit. So I'm going to go to the design or insert, and I'm going to go to shapes, and I'm going to grab a line. And I'm going to try to identify where it starts or it stops becoming proportional, which is probably right around here. I'm going to click and hold shift, and I'm going to move a line to the left. This line is going to intersect with the y-axis, and it's going to give me a perceived load here. So I'll go back down here. I'm going to copy this equation because I have the equation. Now I'm just going to go ahead and substitute for it. So my force, well, if this is 300, this is 350, this is 325, and this is about close to halfway between 300 and 325. So I'll say it's about 313 or 313 pounds, and that's going to be divided by the area, which I calculated up here for my original area, which is this 0.06358. So I'm actually just going to take this number divide it, and this will be inches cubed because I do want to follow this. And if you want the exponent here, you can highlight this and you can superscript it. I would suggest that. I'm going to go ahead and bring down my sigma again by just copying and pasting it, and then I'll actually calculate that out. So that's 1. Going down, we have number 2, which is yield point stress. So it's going to ask, locate the yield point on the test graph and then determine that. This one's not too bad because it's going to be roughly close to the same thing again. So you're going to go ahead and find the yield point, which is a little bit after the proportional limit. It should be somewhere. Should be a little bit more in terms of... So again, we can do the same thing. We can copy and paste this in. This will be roughly around 320 pounds divided by that area which you have up here. And I can just make my life easier, and I can copy and paste things, and then I can eventually just solve for it. And you want to make sure you have the correct units. After number 2, we have the ultimate tensile strength, so the very top part of the graph. So for this one, what I'll do is I'll just draw a line straight across. And then what I'll do is I'll move that line down till I fear where I see it just kind of touches the top of the graph. So about right there. And that again will give me my total load. So again, I can copy and paste this. And I can say that my force, again, probably right around 345 or 345 pounds divided by, again, that original area. And then you can solve for that. Number 4, breaking and rupture point. So for the breaking and rupture point, locate the breaking rupture point on the graph. This one's a little bit misconceiving. You think that the end of the graph is the breaking rupture. It's actually where it stops moving to the right. So it's going to be this spot right here. And again, so I'm going to select that, move it over, and you can see that I'm probably at about 199 pounds. I can go through and I can solve that. Moving to number 5, modulus elasticity. So for modulus elasticity, what it wants to do is I want to solve for all of this. So this one is going to be a little bit interesting. You're going to want to stay within the elastic region of this graph, and you're going to calculate it using this formula. This formula is actually kind of like the slope formula from math. So you're going to identify 2 points. Each point's going to have a force and elongation. So I'll identify those 2 points, and I like to make it easy. So I'll just kind of find, say 100. And then something else that's in the elastic limit would be, say, 200. Put those right there. Then I am going to draw a line down and say this is going to intersect with, right on the graph with the 200, you can see right here, and that's going to give me my second point elongation. I can let's undo that. I will then grab another shape, and I'll move this into place. About right there. And so we kind of just clear this up so it's not too confusing. I'll bring that in a little bit. There we go. So there's my 2 spots. One elongation, the other elongation. So for this equation, this one's a little bit bigger. You could go ahead and copy and paste this, but it's actually its own setup equation that they have in here, where you can kind of move things in. So what you can do is you can copy and paste this, you can double click, and then you can actually just type in some of these values. So if we wanted, we could say force 2 was 200, force 1 on the graph, that would be 100, I made it easy. The elongation 2, so if I go down here, this is 0.01, this is 0.00, so this is 0.005, so maybe 0.007. And then my next one, probably 0.004. And then the area I should have that from before. So this right here was the 0.006, so on. You can type in the full amount. And then the original length, this was the 0.521. Yeah. So that was a 0.521. So I can take all that, I can plug that into there. So yeah, let's just make sure this works. So I'm going to go File. I'm going to close and return to the document. Do I want to save it? Yes. Alright, and then it plugs it in there. And then what you can do is you can go ahead and solve for it, and you can go E equals. Remember to have your correct units and modulus elasticity for this as well. It's going to be part of the grade. So again, kind of two spots, identifying and plugging it in there. Modulus of resilience. This one is this equation right here, which is half of the yield point stress times half of the yield point strain. So up here we identified the yield point. You're going to take that same point, or you could just take this graph that you had. It might be a little bit easier. So if I go ahead and just get rid of this, I can take this graph with this line right here. Select both of those if it's going to let me. I'm not going to sure if it's going to let me. You guys will probably find a workaround for it. I don't have all day. But, you know, somewhere over here. And then you can go ahead and you can find what the strain is at that point. And remember what the strain is. You want the stress. So this stress here is what we've already calculated up here. So you're pretty much just going to take the answer right here, that's stress at the yield point, and then you want strain at the yield point. The strain at the yield point is where you do have to go down. You're going to take a look at the elongation in that case. Remember, it's going to be elongation divided by original length, and you're going to get this. So I'll kind of write this out for you. We'll know this will be 1/2 multiplied by our yield stress. So this number that you get right here, let's just calculate that number real quick. 320. So that's going to give us that number right there. I'm going to go ahead and copy that. Don't need so many decimal spots. And that's going to be multiplied by the strain. So we know that that's going to be, let's see here, 0.01, that's 5, so that's probably about 0.0125. And that's going to be divided by the original length, 0.521. And then you will get the modulus of resilience. Again, take a look at your units to figure out what it should be. If this is in PSI, this is unitless, and it's half, so it's probably still in PSI. And then number 7, what is the modulus of toughness? I'm going to leave this one to you guys because all you have to do is you have to follow it. But to give you an idea, BR stands for breaking point, so it's going to ask you what's the strain at the breaking point, what's the stress at the yield point, you've already figured that out, and then plus 2 times the stress at the ultimate strength, and you've calculated that out already. So you go through and you figure all that out. And then for this graph, modulus of toughness is this entire area. So you're going to want to fill in this entire area to show that. For modulus of resilience, it's going to be this triangle right here. So you want to fill that out. So go back to your notes where it shows you what the portions of the graph are and make sure you identify that out. So it's a really long video. I had to cram it all in 15 minutes. Slow it down, watch it as many times as you need to be able to fill out and finish this document. Thank you.